You did it! You finally got your server running, spun up Prometheus, and successfully connected your monitoring stack. But then you look at the raw data export, and it is a wall of thousands of individual data points. That is when the metric panic sets in. It is incredibly common for beginners to look at this readout, see resources bottoming out, and assume the entire system is failing. You might notice you only have 3.7 gigabytes of free RAM on a 4 gigabyte board, or you see your 1.5 gigahertz CPU inexplicably limping along at 600 megahertz. You have to ask yourself, is the server actively dying, or is this exactly how it is supposed to work? The raw numbers on your dashboard mean nothing on their own. They only make sense if you understand how the underlying operating system manages its hardware. To separate an actual hardware failure from normal, healthy behavior, we need to look at the trade-offs Linux makes between resource utilization and capacity headroom. To do that, we are going to break down the baseline metrics of a Raspberry Pi 4 that is essentially sitting idle. This chart plots metrics across two axes. On the y-axis, how severe it looks, and on the x-axis, actual impact on system health. The cardinal rule of Linux administration: a healthy server intentionally configures itself to look full and slow to maximize efficiency. If you are used to desktop computers where empty resources mean a fast machine, you have to unlearn that habit to read a server dashboard accurately. We'll decode the CPU's behavior, how it manages memory, and the file system's hard limits. Learning to read these true baselines stops you from spending money on unnecessary hardware upgrades to fix problems that do not actually exist. Let's start with the CPU subsystem and the fear that your processor is underperforming. This graph shows dynamic CPU frequency scaling in action. The processor has intentionally dropped from its 1.5 GHz ceiling down to a 600 MHz floor. By downclocking while idle, the system reduces power consumption and keeps temperatures within safe limits, right at 52.5 degrees Celsius. The primary trade-off here is system latency. When unexpected traffic hits the server, the processor needs a fraction of a second to physically spin up to handle the sudden demand. That frequency drop is an instantaneous hardware state. It doesn't tell you how busy the processor actually is. For that, we look to the software concept of load average. Linux tracks load averages across 1-minute, 5-minute, and 15-minute intervals to measure exactly how many processes are waiting for CPU time. On our idle Raspberry Pi, the 1-minute load is 0.24, the 5-minute is 0.09, and the 15-minute load is down to 0.02. Reacting to that 1-minute load average will set you up for constant false alarms. A brief, completely normal background cron job will spike that number and trigger your alerts. You should immediately focus on the 15-minute load average. It filters out the noise and reveals true, sustained processing bottlenecks. Processor speed dictates immediate power efficiency, but that 15-minute load average dictates whether you actually need to buy more processing cores. Now we run into the most common source of dashboard panic, discovering you have almost zero free memory available. This diagram compares the primary ways your system uses RAM. There is a constant push and pull relationship between active and cached memory. Cached memory, sitting at 156 megabytes on our baseline setup, is where the operating system temporarily parks recently used files. Linux intentionally hoards this old data in RAM because reading from memory is exponentially faster than pulling it from the hard drive again. This highly efficient behavior artificially suppresses your top-line free memory metric, causing unnecessary alarm. Then there is active memory, currently occupying 141 megabytes of our board. This represents the exact, unreclaimable amount of RAM your running applications absolutely require to stay alive. If active memory hits the physical hardware limit, the operating system has no choice. It executes catastrophic out-of-memory crashes to protect itself. The rule is simple. Empty RAM is wasted RAM. You have to train yourself to monitor available memory, which includes that easily clearable cache, instead of free memory to accurately assess your system's health. While CPU and RAM are highly dynamic and self-balancing, your file system operates under strict physical limits. You must track the exact number of available bytes remaining on your root partition. If the root file system hits 0 available bytes, core databases and system logs fail to write. The entire operating system will instantly lock up. Unlike your memory or processor, which gracefully degrade and optimize under pressure, File system saturation causes immediate, unrecoverable crashes that demand your manual intervention. A healthy, well-architected Linux server actively optimizes for efficiency by hiding its idle capacity. This checklist outlines a diagnostic framework you can actually rely on. If you are setting up your first home lab, stop alerting on free memory entirely. Track your available memory and your 15-minute load instead. If your 15-minute load is below your physical CPU core count and your temperatures are under 70 degrees, do not intervene. The system is fine. If you are an aspiring sysadmin, true system saturation only occurs when active RAM is pegged near 100% and the CPU frequency never drops back to its 600 MHz minimum. True optimization is not about keeping your dashboard numbers low. It is about knowing exactly when your hardware is genuinely stressed, ensuring you only spend money on upgrades when it is